In previous lecture, we have covered the properties of laser, in which we have discussed about temporal and spatial coherence of light beam. The absorption and emission of photon were also discussed, in which the topic of discussion was the spontaneous and stimulated emission. And in last, we have studied about Einstein's coefficients. In this lecture, we will discuss about Boltzmann distribution law, essential for population inversion, the metastable state and pumping schemes will be discussed. And in the last, the components of laser and the laser process will be discussed. Now, to understand the stimulated emission, it is necessary to know the population of various energy states of an atom. The population of energy states is given by Boltzmann distribution law, which quantitatively relates the probabilities of two states being occupied as n2 equal to n1 exponential minus delta E by kt. Here delta E is E2 minus E1 and n2 and n1 are the number of electrons in excited state and ground state respectively. So this delta E is positive and exponential minus delta E by kt will always be less than 1. So n2 is always less than n1. Or in other words, population of high energy state is less than that of lower energy state. Furthermore, for an atomic radiation, delta E is very greater than kT, where K is Boltzmann coefficient and T is absolute temperature. Thus, in thermal equilibrium, the population of higher energy state is very smaller than that of the ground state. As a result, number of stimulated emission is very less, because to have stimulated emission, electron will have to be in excited energy state. But if somehow we can make N2 greater than N1, the process of stimulated emission dominates over the spontaneous emission and the laser action can be achieved. Since by this equation N2 greater than N1 represents the negative temperature. So this state in which N2 is greater than N1 is also known as negative temperature state. Or this state where N2 is greater than N1 is called the population inversion. Therefore, in the population inversion, the general condition of N1 greater than N2 is inverted into the condition N2 greater than N1. So in normal conditions, the electrons at ground state is more than the number of electrons in excited state. When the system encounters external photon of suitable energy, this photon is absorbed by any electron and that electron make transition to higher energy state. And when number of electrons at excited states are sufficiently large, then the incident photon stimulates the emission of phase coherent photons. So this is the normal population in thermal equilibrium, but in population inversion state we have at least two energy states in which the number of electrons in higher energy state is greater than the number of electrons in lower energy state. But this is not the whole story. Although we have attained higher number of electrons in higher energy state, but what if they will not stay here for more time? As we know that the electrons in higher energy state can stay there up to only 10 nanoseconds. So, if the state of population inversion is not stable enough to give time for incoming photon of required energy to make stimulated emission, then laser will not be produced. So a state with higher lifetime is required to retain the state of population inversion to realize stimulated emission. This state has a higher lifetime of about 1 millisecond, and this state is known as metastable state. So in this example, when the photon hit the electrons at ground state, they will excite to the excited state, and in the way of return, they will encounter another energy state with higher lifetime. So they will stay here for 10 to the power minus 3 seconds, and the population inversion will be achieved between this metastable state and this ground state, like this. Now we shall see the procedure of producing phase coherent photons one by one. Here, very first, the atom is signed by the photons of appropriate energy so that the electrons excite from the ground state to excited state. Remember, there is a metastable state at the energy below the excited state. Next, the electrons in excited state de-excite after 10 nanoseconds and they come to metastable state by releasing small energy. That energy may be high enough to be the photons of light or small enough to heat the system. Next, this metastable state is populated by those electrons and the state of population inversion is found between ground state and the metastable state. Now when some stimulating photon comes along, the de-exciting electrons from metastable state to ground state produce the phase coherent photons, and this is the procedure of producing a laser beam. In this, the first procedure of exciting the electrons from ground state to excited state is important, and this procedure is known as the pumping. We shall study pumping in more detail in next slides. The pumping is a process by which the population inversion can be achieved. In pumping, the excitation of medium atoms is done by supplying a suitable energy. The pumping is a process by which state of population inversion can be achieved. In pumping, the excitation of medium atoms is done by supplying a suitable energy. According to the suitable energy, the pumping can be divided in many types like optical pumping, electrical pumping, and thermal pumping, etc. According to the number of energy states involved in the pumping can be subdivided in two schemes like 3-level pumping scheme and 4-level pumping scheme. In 3-level or 4-level pumping schemes, one or two metastable states are involved. In 3-level pumping scheme, one metastable state is involved, and other two states are the ground state of the atom and one excited state of the atom. In 3-level pumping scheme, electrons in ground state are first excited to high energy level state and then they come to metastable state to create a population inversion state between metastable state and ground state, and laser is produced by transition of electrons from metastable state to ground state. In 4-level pumping scheme, two metastable states are involved. So in this pumping scheme, electrons are excited to high energy state from the ground state, then they de-excite to first metastable state, and the population inversion is achieved between these two metastable states. Laser is produced by stimulated emission between these two metastable states. Let us now discuss laser principle and different parts of laser. There are few conditions for stimulated emission to dominate the other two processes. These are the ratio between B21 and A21 must be very high. It can be achieved by presence of metastable state. And the energy density of incoming photons must be very high. It can be achieved by suitable pumping scheme. Ratio between N2 and N1 must be high, and this is the condition of population inversion achieved by the pumping. Thus, there are three steps required by laser action. The first step is pumping, second step is population inversion achieved by the pumping, and step 3 is stimulated emission. Typically, The spontaneous emission from excited state to metastable state is non-radiative, means the energy difference between excited state and metastable state is very less. These are the main components of a laser. The first is the energy source. The energy source is required to raise the system to an excited state. Second is active medium or working substance. When the active medium is excited by energy provided by energy source, it achieves population inversion. The active material may be the solid or gas. Depending upon this active material, we have different types of laser like solid state laser for solid active medium or gas lasers according to the active medium is gas. The third component of a laser is optical resonator. The optical resonator consists of two mirrors facing each other and exactly parallel to each other. The active material is enclosed by these optical resonators. Out of these two mirrors, one is fully reflective while the other is partially transparent. This is active medium. These are two mirrors where this is fully reflective and this is partially reflective. This region between these two reflectors is known as laser cavity, and the energy is supplied to this active medium for pumping by energy source. And the output beam at the outer face of partially reflective mirror is the beam of laser. This is the active material. Very first, using suitable pumping process, the material in non-excited state is taken into population inversion state, and for this energy source is required. At the initial state, spontaneous photons are emitted and they go in all the directions like this. Since the active material is put in laser cavity consisting of two reflectors, the photons traveling in random directions are lost and the stimulated photons are to be made to pass through the medium a number of times. On reaching the partially reflective mirror, some photons are transmitted out while the remaining are reflected back. The reflected photons de-excite more and more atoms and the beam is now amplified. The amplified beam undergoes multiple reflections at the mirror and gains the strength. Through the partially reflecting mirror, the intense beam goes out as a laser beam.